Some other things that we can tell from where elements sit on the periodic table is how metallic or non-metallic their character is. We define metallic character essentially as the level of reactivity of a metal. The metallic character increases as you go down a group. So that means that as we go down a group, they become more and more reactive. And that hopefully begins to make sense since ionization energies are decreasing as you go down a group. That means there's an increased ability for metals lower in the group to lose their electrons. That essentially makes them much more reactive. So if we look just at the alkali metals, lithium is slightly less reactive than sodium, which is slightly less reactive than potassium. That means francium is the most reactive metal of all metals, but especially clear then that it's the most reactive of the group 1 metals. Having a non-metallic character relates to the tendency to accept electrons because nonmetals tend to be the elements that are most in need of 1 or 2 electrons to complete their valence shell. So nonmetals tend to gain electrons, right, in chemical reactions. So they have a very high attraction for electrons within a compound. The ones that are the most reactive nonmetals are actually the highest and farthest to the right on the table. So fluorine continues to be the winner of all of the categories because fluorine is the smallest with its valence electrons closest to the nucleus. Having a need for only 1, it is very reactive. And as we go down further and further, because those electrons get farther and farther from the nucleus, they, although they are wanted, are not actually quite as easy to gain. So we see then that they are not going to give up as much in terms of electron affinity for gaining those electrons. So metallic character increases as we go down a group. Non-metallic character actually decreases as we go down a group. So this kind of ties together all of the different trends that we have been looking at. All of these are pointing in the direction of increasing. So increasing atomic radius as we go down a group, increasing atomic radius as we go from right to left across a period. Increasing ionization energies to left to right, increasing electron affinities left to right, increasing electron affinity and ionization energy from bottom to top. Having the most non-metallic character are those in the upper right-hand corner, excluding the noble gases, and having the most metallic character, the most willingness to lose an electron, puts things in the bottom left-hand corner. When you are working with ions, one of the things that you may be asked to do is to write the electron configuration for the ion. Now, we have done electron configurations for neutral atoms. We're always able to figure out how many electrons they have by matching it to the atomic number. And we follow Aufbau's principle by using the flowchart, and we write the electron configuration 1s2, 2s2, and so on. To write the electron configuration for an ion is to do exactly the same thing, however, to either add or remove electrons according to the charge. So that may mean that the electron configuration might not have the valence shell that we would expect it to have. Remember that the valence electrons are always located in the highest energy level and orbital. So for example, if we were to take a look at chromium, chromium has a normal electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d4, right? It is in the 4th period. It is the 4th element into the D block. When many students first try to do this, they try to remove the electrons that are listed last. So if chromium were to form a positive 2 ion, that would mean that it would have 2 fewer electrons than normal. So many students would just say at the very end 3d2 instead of 3d4. The problem is those are not in fact the valence electrons for chromium or anything else for that matter in period 4. Energy level 4 happens to be the highest occupied energy level, so those are where the valence electrons are at. Those are the valence electrons we would therefore have to remove. So we would remove 4s2, and we would have a new electron configuration missing the 4s2. So we would have 1s2, 2s2, 2p6, 3s2, 3p6, and 3d4. So taking away the 4s2.